Okay, let me get started for today. So for today, first of all, I'm going to spend a few minutes talking about a couple more neural net concepts, including actually a couple of the concepts that turn up in assignment 2. Then the bulk of today is then going to be moving on to introducing what are language models. And then after introducing language models, we're going to introduce a new kind of neural network, which is one way to build language models, which is recurrent neural networks. They're an important thing to know about, and we use them in assignment 3, but they're certainly not the only way to build language models. In fact, probably a lot of you already know that there's this other kind of neural network called transformers, and we'll get onto those after we've done recurrent neural nets. Talk a bit about problems with recurrent neural networks, and well, if I have time, I'll get onto the recap. Before getting into the content of the class, I thought I could just spend a minute on giving you the stats of who is in CS224N. Who's in CS224N kind of looks like the pie charts they show in CS106A these days. Except more grad students, I guess. So the 4 big groups are the computer science undergrads, the computer science grads, the undeclared undergraduates, and the NDO grads. So this is a large portion of the SCPD students, though some of them are under computer science grads. So that makes up about 60% of the audience. And if you're not in one of those 4 big groups, you're in the other 40%, and everybody is somewhere. So there are lots of other interesting groups down here. So, you know, the bright orange down here, that's where the math and physics PhDs are. Up here, I mean, interestingly, we now have more statistics grad students than there are SimSys undergrads. It didn't used to be that way around in NLP classes. And, you know, one of my favorite groups, the little magenta group down here, these are the humanities undergrads. Yay, humanities undergrads. In terms of years, it breaks down like this. First year grad students are the biggest group, tons of juniors and seniors, and a couple of brave frosh. Are any brave frosh here today? Yeah. Okay, welcome. Yeah, so modern neural networks, especially language models, are enormous. This chart's sort of out of date because it only goes up to 2022, but it's sort of actually hard to make an accurate chart for 2024 because in the last couple of years, the biggest language model makers have in general stopped saying how large their language models are in terms of parameters. But at any rate, they're clearly huge models which have over 100 billion parameters. And so large and then deep in terms of very many layers, neural nets are a cornerstone of modern NLP systems. We're going to be pretty quickly working our way up to look at those kind of deep models. But I just sort of, for starting off with something simpler, you know, I did just want to kind of key you in for a few minutes into a little bit of history, right? So the last time neural nets were popular was in the 80s and 90s, and that was when people worked out the backpropagation algorithm. Jeff Hinton and colleagues made famous the backpropagation algorithm that we've looked at, and that allowed the training of neural nets with hidden layers. And so, but in those days, pretty much all the neural nets with hidden layers that were trained with one hidden layer. You had the input, the hidden layer, and the output, and that's all that there was. And the reason for that was for a very, very long time, people couldn't really get things to work with more hidden layers. So that only started to change in the resurgence of what often got called deep learning, but anyway, back to neural nets. started around 2006, and this was one of the influential papers at the time, Greedy Layer-Wise Training of Deep Neural Networks by Yoshua Bengio and colleagues. And so right at the beginning of that paper, they observed the problem. However, until recently, it was believed too difficult to train deep multi-layer neural networks. Empirically, deep networks were generally found to be not better, and often worse, than neural networks with one or two hidden layers. Jerry Tesoro was actually a faculty member who worked very early on autonomous driving with neural networks. As this is a negative result, there's not been much reported in the machine learning literature. So that really, although people had neural networks and backpropagation and recurrent neural networks we're going to talk about today, that for a very long period of time, 15 years or so, things seemed completely stuck in that you couldn't, although in theory it seemed like deep neural networks should be promising, in practice they didn't work. And so it really then took some new developments that happened in the late 2000s decade and then more profoundly in the 2010s decade to actually figure out how we could have deep neural networks that actually working far better than the shallow neural networks and leading into the networks that we have today. And, we're going to be starting to talk about some of those things in this class and coming up with classes. And I mean, I think, the tendency when you see the things that got neural networks to work much better, like the natural reaction is to sort of shrug and be underwhelmed and think, oh, is this all there is to it? This doesn't exactly seem like difficult science. And in some sense, that's true. They're fairly little introductions of new ideas and tweaks of things, but nevertheless, a handful of little ideas and tweaks of things turn things around from a field that was sort of stuck for 15 years going nowhere and which nearly everyone had abandoned because of that, to suddenly turning around and there being the ability to train these deeper neural networks which then behaved amazingly better as machine learning systems than other things that had preceded them and dominated for the intervening time. So that took a lot of time. So what are these things? One of them, which you can greet with a bit of a yawn in some sense, is doing better regularization of neural nets. So regularization is the idea that beyond just having a loss that we want to minimize in terms of describing the data, we want to, in some other ways, manipulate what parameters we learn so that our models work better. And so normally we have some more complex loss function that does some regularization. The most common way of doing this is what's called L2 loss, where you add on this parameters squared term at the end. And this regularization says, it'd be kind of good to find a model with small parameter weights. So you should be finding the smallest parameter weights that will explain your data well. And there's a lot you can say about regularization, these kind of losses. They get talked about a lot more in other classes like CS224N machine learning. And so I'm not going to say very much about it. This isn't a machine learning theory class. But I do just want to sort of put in one note that's sort of very relevant to what's happened in recent neural networks work. So the classic view of regularization was we needed this kind of regularization to prevent our networks from overfitting, meaning that they would do a very good job at modeling the training data, but then they would generalize badly to new data that was shown. And so the picture that you got shown was this, that as you train on some training data, your error necessarily goes down. However, after some point, you start learning specific properties of things that happen to turn up in those training examples, and that you're learning things that are only good for the training examples, and so they won't generalize well to different pieces of data you see at test time. So if you have a separate validation set or a final test set, and you traced out the error or loss on that validation or test set, that after some point it would start to go up again. This is a quirk in my bad PowerPoint. It's just meant to go up. And the fact that it goes up is then you have overfit your training data. And making the parameters numerically small is meant to lessen the extent to which you overfit on your training data. This is not a picture that modern neural network people believe at all. Instead, the picture has changed like this. We don't believe that overfitting exists anymore, but what we are concerned about is models that will generalize well to different data. So that when we train, so in classical statistics, the idea that you could train billions of parameters like large neural nets now have would be seen as ridiculous because you could not possibly estimate those parameters well, and so you just have all of this noisy mess. But what's actually been found is that, yeah, it's true you can't estimate the numbers well, but what you get is a kind of an interesting averaging function from all these myriad numbers. And if you do it right, what happens is as you go on training, that for a while it might look like you're starting to overfit, but if you keep on training in a huge network, not only will your training loss continue to go down very infinitesimally, but your validation loss will go down as well. And so that on huge networks these days, we train our models so that they overfit to the training data almost completely, right? So that if you train a huge network now on a training set, you can essentially train them to get zero loss. Maybe it's 0.000007 loss or something, but you can train them to get zero loss because you've got such rich models, you can perfectly memorize the entire training set. Now, classically, that would have been seen as a disaster because you've overfit the training data. With modern large neural networks, it's not seen as a disaster because providing you've done regularization well, that your model will also generalize well to different data. However, the flip side of that is normally this kind of L2 regularization or similar ones like L1 regularization aren't strong enough regularization to achieve that effect. And so neural network people have turned to other methods of regularization, of which everyone's favorite is dropout. So this is one of the things that's on the assignment. And at this point, I should apologize or something, because the way dropout is done, the way dropout is presented here is sort of the original formulation. The way dropout is presented on the assignment is the way it's now normally done in deep learning packages. So there are a couple of details that vary a bit, and let me just present the main idea here and not worry too much about the details of the math. So the idea of dropout is at training time, every time you are doing a piece of training with an example, what you're going to do is inside the middle layers of the neural network, you're just going to throw away some of the inputs. And so technically the way you do this is you have a random mask that you sample each time of zeros and ones. You do a Hadamard product of that with the data. So some of the data items go to zero. And you have different masks each time. So for the next thing, I've now masked out something different this time. And so you're just sort of randomly throwing away the inputs. And the effect of this is that you're training the model that it has to be robust and work well and make as much use of every input as it can. It can't decide that it can be extremely reliant on component 17 of the vector, because sometimes it's just going to randomly disappear. So if there are other features that you could use instead that would let you work out what to do next, you should also know how to make use of those features. So at training time, you randomly delete things. At test time, sort of for efficiency, but also quality of the answer, you don't delete anything. You keep all of your weights, but you just rescale things to make up for the fact that you used to be dropping things. Okay, there are several ways that you can think of explaining this. One motivation that's often given is that this prevents feature co-adaptation. So rather than a model being able to learn complex functions of feature 7, 8, and 11 can help me predict this, it knows that some of the features might be missing, so it has to sort of make use of things in a more flexible way. Another way of thinking of it is that there's been a lot of work on model ensembles where you can sort of mix together different models and improve your results. If you're training with Dropout, it's kind of like you're training with a huge model ensemble, because you're training with the ensemble of the power set, the exponential number of every possible dropout of features all at once, and that gives you a very good model. So there are different ways of thinking about it. I mean, if you've seen naive Bayes and logistic regression models before, I kind of think a nice way to think of it is that it gives us sort of a middle ground between the two, because for naive Bayes models, you're weighting each feature independently, just based on the data statistics, doesn't matter what other features are there. In a logistic regression, weights are set in the context of all the other features, and with Dropout, you're somewhere in between. You're setting the weights in the context of some of the other features, but different ones will disappear at different times. But following work that was done at Stanford by Stefan Varga and others, that generally these days people regard Dropout as a form of feature-dependent regularization, and he shows some theoretical results as to why to think of it that way. Okay, I think we've implicitly seen this one, but vectorization is the idea, no for loops, always use vectors, matrices, and tensors, right? The entire success and speed of deep learning works from the fact that we can do things with vectors, matrices, and tensors. So, if you're writing for loops in any language, but especially in Python, things run really slowly. If you can do things with vectors and matrices, even on CPU, things run at least an order of magnitude faster. And well, what everyone really wants to move to doing in deep learning is running things on GPUs, or sometimes now neural processing units, and then you're getting 2-3 orders of magnitude of speed up. So do always think about, I should be doing things with vectors and matrices. If I'm writing a for loop for anything that isn't some very superficial bit of input processing, I've almost certainly made a mistake, and I should be working out how to do things with vectors and matrices. And that's kind of things like Dropout. You don't want to write a for loop that goes through all the positions and sets some of them to 0. You want to be sort of using a vector operation with your mask. 2 more, I think. Parameter initialization. I mean, this one might not be obvious, but when we start training our neural networks, in almost all cases, it's vital that we initialize the parameters of our matrices to some random numbers. And the reason for this is if we just start with our matrices all 0 or some other constant, normally the case is that we have symmetry. So it's sort of like in this picture when you're starting on this saddle point, that, you know, it's symmetric to the left and the right, and or whatever, forward and backwards and left and right. And so you sort of don't know where to go, and you might be sort of stuck and stay in the one place. I mean, normally a way to think about it is the operations that you're doing to all the elements in the matrix are sort of the same. So rather than having, you know, a whole vector of features, if all of them have the same value initially, often it's sort of like you only have one feature and you've just got a lot of copies of it. So to initialize learning and have things work well, we almost always want to set all the weights to very small random numbers. And so at that point, you know, when I say very small, we sort of want to make them in a range so that they don't disappear to zero if we make them a bit smaller, and they don't sort of start blowing up into huge numbers when we multiply them by things. And doing this initialization at the right scale used to be seen as something pretty important, and there were particular methods that had a basis of sort of thinking of what happens once you do matrix multiplies that people had worked out and often used. One of these was this Javier initialization, which was sort of working out what variance of your uniform distribution to be using based on the sort of number of inputs and outputs of a layer and things like that. The specifics of that, you know, I think we still use to initialize things in this assignment 2, but we'll see later that they go away because people have come up with cleverer methods, in particular doing layer normalization, which sort of obviates the need to be sort of careful on the initialization, but you still need to initialize things to something. Okay, then the final one, which is also something that appears in the second assignment that I just want to say a word about, was optimizers. So we talked about in class stochastic gradient descent and did the basic equations for stochastic gradient descent. And, you know, to a first approximation, there's nothing wrong with stochastic gradient descent. And if you fiddle around enough, you can usually get stochastic gradient descent actually to work well for almost any problem. But getting it to work well is very dependent on getting the scales of things right, of sort of having the right step size, and often you have to have a learning rate schedule with decreasing step sizes and various other complications. So people have come up with more sophisticated optimizers for neural networks. And for complex nets, sometimes these seem kind of necessary to get them to learn well, and at any rate, they give you sort of lots of margins of safety since they're much less dependent on you setting different hyperparameters right. And the idea of all the methods I mentioned and the most commonly used methods is that for each parameter, they're accumulating a measure of what the gradient has been in the past, and they've got some idea of the scale of the gradient, the slope for a particular parameter, and then they're using that to decide how much you move the learning rate at each time step. So the simplest method that was come up was this one called AdaGrad. If you know John Ducci and EE, he was one of the co-inventors of this. You know, it's simple and nice enough, but it tends to stall early. Then people came up with different methods. Adam's the one that's on assignment 2. It's a really good, safe place to start. But in a way, sort of our word vectors have a special property because of their sparseness, that, you know, you're very sparsely updating them because particular words only turn up occasionally. So people have actually come up with particular optimizers that sort of have special properties for things like word vectors. And so these ones with the W at the end can sometimes be good to try. And then, you know, again, there's a whole family of extra ideas that people have used to improve optimizers. And if you want to learn about that, you can go off and do an optimization class like convex optimization. But there are ideas like momentum and Nesterov acceleration and things like that. And all of those things people also variously try to use. But Adam is a good name to remember if you remember nothing else. Okay, that took longer than I hoped. But I'll get on now to language models. Okay, language models. So, you know, in some sense, language model is just two English words, but when in NLP we say language models, we mean it as a technical term that has a particular meaning. So the idea of a language model is something that can predict, well, what word is going to come next, or more precisely, it's going to put a probability distribution over what words come next. So the students opened there, what words are likely to come next? Bags. Laptops.
Notebooks.
Notebooks, yes. I have some of those at least. Okay. Yeah, I mean, so these are kind of likely words, and if on top of those we put a probability on each one, then we have a language model. So formally, we've got a context of preceding items. We're putting a probability distribution over the next item, which means that the sum of the estimates of this for all the items in the vocabulary will sum to 1. And if we've defined a P like this that predicts probabilities of next words, that is called a language model, as it says here. An alternative way that you can think of a language model is that a language model is a system that assigns a probability to a piece of text. And so we can say that a language model can take any piece of text and give it a probability. And the reason we can do that is we can use the chain rule. So if I want to know the probability of any stretch of text, I say, given my previous definition of language model, easy, I can do that. Probability of x1 with a null preceding context times the probability of x2 given x1, etc. along. I can do this chain rule decomposition, and then the terms of that decomposition are precisely what the language model, as I defined it previously, provides. Okay, so language models are this essential technology for NLP. Just about everything from the simplest places forward, where people do things with human language and computers, people use language models. In particular, you know, they weren't something that got invented in 2022 with ChatGPT. Language models have been central to NLP at least since the 80s. The idea of them goes back to at least the 50s. So anytime you're typing on your phone and it's making suggestions of next words, regardless of whether you like those suggestions or not, those suggestions are being generated by a language model. Traditionally a compact, not very good language model, so it can run sort of quickly and very little memory in your keyboard application. If you go on Google and you start typing some stuff, and it's telling you stuff that could come after it to complete your query, well, again, that's being generated by a language model. So how can you build a language model? So before getting into neural language models, I've got just a few slides to tell you about the old days of language modeling. So this is sort of how language models were built from 1975 until, you know, effectively around about 2012. So we want to put probabilities on these sequences, and the way we're going to do it is we're going to build what's called an n-gram language model. And so this is meaning we're going to look at short word subsequences and use them to predict. So n is a variable describing how short are the word sequences that we're going to use to predict. So if we just look at the probabilities of individual words, we have a unigram language model. If we look at probabilities of pairs of words, bigram language model. probabilities of 3 words, trigram language models. Probabilities of more than 3 words, they get called 4-gram language models, 5-gram language models, 6-gram language models. So for people with a classics education, this is horrific, of course. In particular, not even these ones are correct because gram is a Greek root, so it should really have Greek numbers in front here. So you should have monograms and digrams. And, you know, actually, so the first person who introduced the idea of n-gram models was actually Claude Shannon when he was working out information theory, the same guy that did cross-entropy and all of that. And if you look at his 1951 paper, he uses digrams. But the idea died about there, and everyone else, this is what people say in practice. It's kind of cute. I like it, a nice, you know, practical notation. So to build these models, the idea is, look, we're just going to count how often different n-grams appear in text and use those to build our probability estimates. And in particular, our trick is that we make a Markov assumption so that if we're predicting the next word based on a long context, we say, tell you what, we're not going to use all of it. We're only going to use the most recent n-1 words. So we have this big context and we throw most of it away. And so if we're predicting word xt plus 1 based on simply the preceding n-1 words, well, then we can make the prediction using n-grams for, whatever it is, if we use n is 3, would have a trigram here and normalized by a bigram down here, and that would give us relative frequencies of the different terms. So we can do that simply by counting how often n-grams occur in a large amount of text and simply dividing through by the counts, and that gives us a relative frequency estimate of the probability of different continuations. Does that make sense? Yeah, that's a way to do it. Okay, so suppose we're learning a 4-gram language model, right? And we've got a piece of text. As the proctor started the clock, the students opened there. So, well, to estimate things, we are going to throw away all but the preceding 3 words. So we're going to estimate based on students open there. And so we're going to work out the probabilities by looking for counts of students open there W and counts of students open there. So we might have in a corpus that students open there occurred 1,000 times, students open there books occurred 400 times, and so we'd say the probability estimate is simply 0.4 for books. If exams occurred 100 times, the probability estimate is 0.1 for exams. And, well, you can sort of see that this is bad. It's not terrible, because if you are going to try and predict the next word in a simple way, looking at the immediately prior words are the most helpful words to look at. But it's clearly sort of primitive, because, you know, if you'd known that the prior text was as the proctor started the clock, that makes it sound likely that the words should have been exams. Where since you're estimating just based on students open theirs, well, you'd be more likely to choose books because it's more common. So it's a kind of a crude estimate, but it's a decent enough place to start. It's a crude estimate that could be problematic in other ways. I mean, why else might we kind of get into troubles by using this as our probability estimate? Yeah? There are too many n-grams. So there are a lot of n-grams. Yeah, so there are a lot of words, and therefore there are a lot of n-grams. Yeah, so that's a problem. We'll come to it later. Anything else? Maybe up the back?
Like the word W might not even show up in the training data, so you might just have a count 0 for that.
Yeah. Yeah. So if we're counting over any reasonable size corpus, there are lots of words that we just are not going to have seen, right? That they never happen to occur in the text that we counted over, so if you start thinking students open there, there are lots of things that you could put there, students open their accounts, or if the students are doing dissections in a biology class, maybe students open their frogs, I don't know. That there are lots of words that in some context, would actually be possible, and lots of them that we won't have seen, and so it gives them a probability estimate of 0. And that tends to be an especially bad thing to do with probabilities, because once we have a probability estimate of 0, any computations that we do that involve that will instantly go to 0. So we have to deal with some of these problems. So for that sparsity problem, right, that we could have the word never occurred in the numerator, and so simply done, we get a probability estimate of 0. The way that was dealt with was that people just hacked the counts a little to make it non-zero. So there are lots of ways that are explored, but the easiest way is you just sort of added a little delta, like 0.25 to counts. So things that you never saw got a count of 0.25 in total, and things you saw once got a count of 1.25, and then there are no zeros anymore. Everything is possible. You could think then there's a second problem that, wait, you might never have seen students open there before, and so that means your denominator is just undefined and you don't have any counts in the numerator either. So you sort of need to do something different there. And the standard trick that was used then was that you did back off. So if you couldn't estimate words coming after students open there, you just worked out the estimates for words coming after open there. And if you couldn't estimate that, you just used the estimate of words coming after there. So you used less and less context until you could get an estimate that you could use. But something to note is that we've got these conflicting pressures now, so that on the one hand, if you want to come up with a better estimate, that you would like to use more context, i.e. to have a larger n-gram. But on the other hand, as you use more conditioning words, well, the storage size problem someone mentioned gets worse and worse because the number of n-grams that you have to know about is going up exponentially with the size of the context. But also your sparseness problems are getting way, way worse, and you're almost necessarily going to be ending up seeing zeros. And so because of that, in practice where things tended to sort of max out was 5. And occasionally people use 6 grams and 7 grams, but most of the time, between the sort of sparseness and the cost of storage, 5 grams was the largest thing people dealt with. Famous resource from back in the 2000s decade that Google released was Google Ngrams, which was built on a trillion word web corpus and had counts of n-grams, and it gave counts of n-grams up to n equals 5, and that is where they stopped. Okay, well, we've sort of said the storage problem. The storage problem is, well, to do this, you need to store these counts. The number of counts is going up exponentially in the amount of context size. But what's good about n-gram language models? They're really easy to build. You can build one yourself in a few minutes when want to have a bit of fun on the weekend. All you have to do is start sort of storing these counts for n-grams, and you can use them to predict things. So, at least if you do it over a small corpus, like a couple of million words of text, you can build an n-gram language model in seconds on your laptop. Well, you have to write the software. Okay, a few minutes to write the software, but building the model takes seconds because, there's no training in neural network. All you do is count how often n-grams occur. And so once you've done that, you can then run an n-gram language model to generate text. We could do text generation before ChatGPT, right? So if I have a trigram language model, I can start off with some words, today, the, and I could look at my stored n-grams and get a probability distribution over next words. And here they are. You know, note the strong patterning of these probabilities, because remember they're all derived from counts, right, that are being normalized. So really, these are words that occurred once. These are words that occurred twice. These are words that occurred 4 times in this context, right? So they're sort of in some sense crude when you look at them more carefully. But so what we could do is then at this point, you know, we roll a die and get a random number from 0 to 1, and we can use that to sample from this distribution. So we sample from this distribution, and so that if we sort of generate sort of as our random number something like 0.35, if we go down from the top, we'd say, okay, we've sampled the word price, today the price, and then we repeat over, we condition on that, we probability distribution of the next word, we generate a random number and use it to sample from the distribution, we can say generate 0.2, and so we choose of, we now condition on that, we get a probability distribution, we generate a random number which is 0.5 or something, and so we get gold coming out, and we can say today the price of gold. And we can keep on doing this and generate some text. And so here's some text generated from 2 million words of training data using a trigram language model. Today, the price of gold per tonne, while production of shoe lasts in shoe industry, the bank intervened just after it considered and rejected an IMF demand to rebuild depleted European stocks. September 3rd, in primary 76 cents a share. Now, okay, that text isn't great, but you know, I actually want people to be in a positive mood today, and you know. Actually, it's not so bad, right? It's sort of surprisingly grammatical. I mean, in particular, like I lowercased everything, so this is the IMF that should be capitalized of the International Monetary Fund, right? You know, there are big pieces of this that even make sense, right? The bank intervened just after it considered and rejected an IMF demand. You know, that's pretty much making sense as a piece of text, right? So it's mostly grammatical. It looks like, English text. I mean, it makes no sense, right? It's sort of really incoherent. So there's work to do, but, what was already, you could see, there's even these simple n-gram models, you could, from a very low level, you could kind of approach what text in human language worked like in from below. And, I could easily make this better even with the n-gram language model because, rather than 2 million words of text, if I trained on 10 million words of text, it'd be better. If I then, rather than a trigram model, could go to a 4-gram model, it'd get better. And you'd sort of start getting better and better approximations of text. And so this is essentially what people did until about 2012. And, really, the same story that people tell today, that scale will solve everything, is exactly the same story that people used to tell in the early 2010s with these n-gram language models. If you weren't getting a good enough results with your 10 million words of text in a trigram language model, the answer was that if you had 100 million words of text in a 4-gram language model, you'd do better. And then if you had 1 trillion words of text in a 5-gram language model, you'd do better. And gee, wouldn't it be good if we could collect 10 trillion words of text so we could train an even better n-gram language model? Same strategy. But it turns out that sometimes you can do better with better models as well as simply scale. And so things got reinvented and started again with building neural language models. So how can we build a neural language model? So, we've got the same task of having a sequence of words and we want to put a probability estimate over what word comes next. And so the simplest way you could do that, which you'll hopefully have all have thought of because it connects what we did in earlier classes. Look, we already had this idea that we could represent a context by the concatenation of some word vectors, and we could put that into a neural network, and we could use that to predict something. And in the example I did in the last couple of classes, what we used it to predict was, is the center word a location or not a location? Just a binary choice. But that's not the only thing we could predict. We could have predicted lots of things with this neural network. We could have predicted whether the piece of text was positive or negative. We could have predicted whether it was written in English or Japanese. We could predict lots of things. So one thing we could choose to predict is we could choose to predict what word is going to come next after this window of text. We'd have a model just like this one, apart from up the top, instead of doing this binary classification, we'd do a many way classification over what is the next word that is going to appear in the piece of text. And that would then give us a neural language model. In particular, it'd give us a fixed window neural language model. So that we'd do the same Markov assumption trick of throwing away the further back context. And so for the fixed window, we'll use word embeddings, which you can concatenate. We'll put it through a hidden layer, and then we'll take the output of that hidden layer, multiply it by another layer, say, and then put that through a softmax and get an output distribution. And so this gives us sort of a fixed window neural language model. And apart from the fact that we're now doing a classification over many classes, this is exactly like what we did last week. So it should look kind of familiar. It's also kind of like what you're doing for assignment 2. And so this is essentially the first kind of neural language model that was proposed. So in particular, Yoshua Bengio really sort of right at the beginning of the 21st century suggested that you could do this, that rather than using an n-gram language model, you could use a fixed window neural language model. And even at that point, he and colleagues were able to get some positive results from this model. But at the time, it wasn't widely noticed. It didn't really take off that much. And it was sort of for a combination of reasons. When it was only a fixed window, it was sort of not that different to n-grams in some sense. And although the neural network could give better generalization, it could be argued, rather than using counts. I mean, in practice, neural nets were still hard to run without GPUs, and people felt, and I think in general this was the case, that you could get more oomph by doing the scale story and collecting your n-gram counts on hundreds of billions of words of text rather than trying to make a neural network out of it. And so it didn't really sort of especially take off at that time. But in principle it seemed a nice thing. It got rid of the sparsity problem. It got rid of the storage costs. You no longer have to store all observed n-grams. You just have to store the parameters of your neural network. But it didn't solve all the problems that we'd like to solve. So in particular, we still have this problem of the Markov assumption that we're just using a small fixed context beforehand to predict from. And there are some disadvantages to enlarging that window. And there's no fixed window that's ever big enough. There's another thing that, if you look technically at this model, that might sort of make you suspicious of it, which is, when we have words in different positions, that those words in different positions will be treated by completely different subparts of this matrix W. So you might think that, okay, for predicting that books comes next, the fact that this is a student is important, but it doesn't matter so much exactly where the word student occurs, right? The context could have been the students slowly open there, and it's still the same students. We've just got a bit different linguistic structure, where this W matrix would be using completely separate parameters to be learning stuff about student here versus student in this position. So that seems kind of inefficient and wrong. And so that suggested that we kind of need a different kind of neural architecture that can process any length of input and can use the same parameters to say, hey, I saw the word student. That's evidence that things like books, exams, homework will be turning up regardless of where it occurs. And so that then led to exploration of this different neural network architecture called recurrent neural networks, which is what I'll go on to next. But before I do, is everyone basically okay with what a language model is? Yeah. No questions? Okay. Recurrent neural networks. So recurrent neural networks is a different family of neural networks. So effectively in this class, we see several neural network architectures. So in some sense, the first architecture we saw was word-to-vec. It's a sort of a very simple encoder-decoder architecture. The second family we saw was feed-forward networks or fully connected layer classic neural networks. And the third family we're going to see is recurrent neural networks, which have different kinds. And then we'll go on to transformer models. Okay, so the idea of a recurrent neural network is that you've got one set of weights that are going to be applied through successive moments in time, i.e. successive positions in the text. And as you do that, you're going to update the parameters as you go. We'll go through this in quite a bit of detail, but here's the idea of it. So we've got the students open there, and we want to predict with that. And the way that we're going to do it, okay, I've still got 4 words in my example, so I can put stuff down the left side of the slide, but there could have been 24 words with recurrent neural networks because they can deal with any length of context. Okay, so as before, our words start off as just words or one-hot vectors, and we can look up their word embeddings just like before. Okay, but now to compute probabilities for the next word, we're going to do something different. So our hidden layer is going to be recurrent. And by recurrent, it means we're going to sort of change a hidden state at each time step as we proceed through the text from left to right. So we're going to start off with an H0, which is the initial hidden state, which can actually just be all zeros. And then at each time step, what we're going to do is we're going to multiply the previous hidden state by a weight matrix. We're going to take a word embedding and multiply it by a weight matrix. And then we're going to sum the results of those two things, and that's going to give us a new hidden state. So that hidden state will then sort of store a memory of everything that's been seen so far. So we'll do that, and then we'll continue along. So we'll multiply the next word vector by the same weight matrix WE. We store multiply the previous hidden state by the same weight matrix WH, and we add them together and get a new representation. I've only sort of said this bit, so I've left out a bit. Commonly, there are 2 other things you're doing. You're adding on a bias term, because we usually separate out a bias term, and you're putting things through a nonlinearity, so I should make sure I mention that. And for recurrent neural networks, most commonly, this nonlinearity has actually been the tan H function, so it's sort of balanced on the positive and negative side. And so you keep on doing that through each step, And so the idea is once we've gotten to here, this H4's hidden state is a hidden state that in some sense has read the text up until now. It's seen all of the students open there. And if the word students occurred in any of these positions, it will have been multiplied by the same WE matrix and added into the hidden state. So it's kind of got a cleaner, low parameter way of incorporating in the information that it's seen. So now I want to predict the next word, and to predict the next word, I'm then going to do, based on the final hidden state, the same thing I did before. So I'm going to multiply that hidden state by a matrix and add another bias and stick that through a softmax and use that to sample from that softmax. Well, the softmax will give me a language model, a probability over all next words, and I can sample from it to generate the next word. That makes sense? Okay, recurrent neural networks. So for recurrent neural networks, we can now process any length of preceding context, and we'll just put more and more stuff in our hidden state. So our computation is using information from many steps back. Our model size doesn't increase for having a long context, right? We have to do more computation for a long context, but our representation of that long context just remains this fixed size hidden vector h of whatever dimension it is. So there's no exponential blowout anymore. There's the same weights applied in every time step, so there's a symmetry in how inputs are processed. There are some catches. The biggest catch in practice is that recurrent computation is slow. So for the feed-forward layer, we just had our input vector, we multiplied it by a matrix, we multiplied it by a matrix however many times, and then at the end we're done. Whereas here, we've sort of stuck with this sequentiality that you have to be doing one hidden vector at a time. In fact, this is going against what I said at the beginning of class, because essentially here you're doing a for loop. You're going through for time equals 1 to t, and then you're generating in term each hidden vector. And that's one of the big problems with RNNs that have led them to fall out of favor. There's another problem that we'll look at more, is that in theory, this is perfect. You're just incorporating all of the past context in your hidden vector. In practice, it tends not to work perfectly because, although stuff you saw back here is in some sense still alive in the hidden vector as you come across here, that your memory of it gets more and more distant, and it's the words that you saw recently that dominate the hidden state. Now, in some sense, that's right, because the recent stuff is the most important stuff that's freshest in your mind. It's the same with human beings. They tend to forget stuff from further back as well. But RNNs, especially in the simple form that I've just explained, forget stuff from further back rather too quickly. And we'll come back to that again in Thursday's class. Okay, so for training an RNN language model, the starting off point is we get a big corpus of text again, and then we're going to compute for each time step a prediction of the probability of next words. And then there's going to be an actual next word, and we're going to use, that as the basis of our loss. So our loss function is the cross entropy between the predicted probability and what the actual next word that we saw is, which again, as in the example I showed before, is just the negative log likelihood of the actual next word. Ideally, you'd like to predict the actual next word with probability 1, which means the negative log of 1 would be 0, and there'd be no loss. But in practice, if you give it an estimate of 0.5, there's only a little bit of loss, and so on. And so to get our overall objective function, we work out the average loss, the average negative log likelihood of predicting each word in turn. So showing that as pictures, if our corpus is the students open their exams, we're first of all going to be trying to predict, what comes after the, and we will predict some word with different probabilities, and then we'll say, oh, the actual next word is students. Okay, you gave that a probability of 0.05, say, because all we know was that the first word was the. Okay, there's a loss for that, the negative log prob given to students. We then go on and generate the probability estimate over the next words, and then we say, well, the actual word is opened. What probability estimate did you give to that? We get a negative probability loss. Keep on running this along, and then we sum all of those losses and we average them per word, and that's our sort of average per word loss, and we want to make that as small as possible. And so that's our training mechanism. And it's important to notice that, for generating this loss, we're not just doing free generation. We're not just saying to the model, oh, go off and generate a sentence. What we're actually doing is at each step, we're effectively saying, okay, the prefix is the students opened. What probability distribution do you put on next words after that? Generate it with our recurrent neural network, and then ask for the actual next word, what probability estimate did you give to there? And that's our loss. But then what we do is stick there into our recurrent neural network the right answer. So we always go back to the right answer, generate probability distribution for next words, and then ask, okay, what probability did you give to the actual next word exams? And then again, we use the actual next word. So we do one step of generation, then we pull it back to what was actually generated, what was actually in the text, and then we ask it for guesses over the next word and repeat forever. And so the fact that we don't do free generation, but we pull it back to the actual piece of text each time, makes things simple because we sort of know what the actual author used for the next word. And that process is called teacher forcing. And so the most common way to train language models is using this kind of teacher forcing method. I mean, it's not perfect in all respects because, we're not actually exploring different things the model might want to generate on its own and seeing what comes after them. We're only doing the tell me the next word from some human-generated piece of text. Okay, so that's how we get losses, and then after that, we want to, as before, use these losses to update the parameters of a neural network. Okay, and how do we do that? Well, in principle, we just have all of the text that we've collected, which you could think of as just a really long sequence of, okay, we've got 1 billion words of text, here it is, right? So in theory, you could just run your recurrent neural network over your 1 billion words of text, updating the context as you go. But that would make it very difficult to train a model because you'd be accumulating these losses for 1 billion steps and you'd have to store them, and then you'd have to store hidden states so you could update parameters, and it just wouldn't work. So what we actually do is we cut our training data into segments of a reasonable length, and then we're going to sort of run our recurrent neural network on those segments, and then we're going to compute a loss for each segment, and then we're going to update the parameters of the recurrent neural network based on the losses that we found for that segment. I describe it here as the segments being sentences of documents, which seems a linguistically nice thing. It turns out that in recent practice, when you're wanting to scale most efficiently on GPUs, people don't bother with those linguistic niceties. They just say, a segment is 100 words. Just cut every 100 words. And the reason why that's really convenient is you can then create a batch of segments, all of which are 100 words long, and stick those in a matrix and do vectorized training more efficiently, and things go great for you. Okay, but there's still a few more things that we need to know to get things to work great for you. I'll try and get a bit more through this before today ends. So we sort of need to know about how to work out the derivative of our loss with respect to the parameters of our recurrent neural network. And the interesting case here is, these WH parameters are sort of being used everywhere through the neural network at each stage, as are the WE ones. So they appear at many places in the network. So how do we work out the partial derivatives of the loss with respect to the repeated weight matrices? And the answer to that is, it's really simple. You can just sort of pretend that those WHs in each position are different and work out the partials with respect to them at one position. And then to get the partials with respect to WH, you just sum whatever you found in the different positions. And so that is sort of, okay, the gradient with respect to repeated weight is the sum of the gradient with respect to each time it appears. And the reason why that is, it sort of follows what I talked about in lecture 3, that we talk, or you can also think about it in terms of what you might remember from multivariable chain rules. But the way I introduced in lecture 3 is that gradients sum at outward branches. And so what you can think about it in a case like this is that you've got a WH matrix which is being copied by identity to WH1, WH2, WH3, WH4, etc. at each time step. And so since those are identity copies, they have a partial derivative with respect to each other of 1. And so then we apply the multivariable chain rule to these copies. And so we've then got an outward branching node, and you're just summing the gradients to get the total gradient of each time for the matrix. Okay. Yeah, there's one other trick that's perhaps worth knowing. If you've got sort of segments that are 100 long, a common speed up is to say, maybe we don't actually have to run backpropagation for 100 time steps. Maybe we could just run it for 20 time steps and stop, which is referred to as truncated backpropagation through time. In practice, that tends to be sufficient. Note in particular, you're still on the forward pass, updating your hidden state using your full context, but in the backpropagation, you're just sort of cutting it short to speed up training. Okay, so just as I did before with an n-gram language model, we can use RNN language model to generate text. And it's pretty much the same idea, except now we're sort of, rather than just using counts of n-grams, we're using the hidden state of our neural network to give us the input to a probability distribution that we can then sample from. So I can start with the initial hidden state. I can use the start of sentence symbol. In the example I had before, I started immediately with the, hoping that was less confusing the first time. But what you should have asked is, wait a minute, where did the come from? So normally what we actually do is use a special start of sequence symbol like this angle bracketed S. And so we sort of feed it in as a pseudo word, which has a word embedding. And then we, based on this, will be generating first words of the text. So we end up with some representation from which we can sample and get the first word. So now we don't have any actual text. So what we're going to do is take that generated word that we generated and copy it down as the next input. And then we're going to run a next stage of neural network, sample from the probability distribution, a next word favorite, copy it down as the next word of the input, and keep on generating. And so this is referred to as a rollout, that you're kind of continuing to roll the dice and generate forward and generate a piece of text. And so, and normally you want to stop at some point, and the way we can stop at some point is we can have a second special symbol, the angle brackets /s, which says end of your sequence. So we can generate an end of sequence symbol, and then we can stop. And so using this, we can sort of generate pieces of text. And essentially, this is exactly what's happening if you use something like ChatGPT, right? That the model is a more complicated model that we haven't yet gotten to, but it's generating the response to you by doing this kind of process of generating a word at the time, treating it as an input, and generating the next word, and generating this sort of rollout. And that's why, and it's done probabilistically, so if you do it multiple times, you can get different answers. We haven't yet gone to ChatGPT, but we can have a little bit of fun. So you can take this simple recurrent neural network that we've just built here, and you can train it on any piece of text and get it to generate stuff. So for example, I can train it on Barack Obama's speeches. So that's a small corpus, right? He didn't talk that much, right? I've only got a few 100,000 words of text. It's not a huge corpus. I'll just show this and then I can answer the question. But I can generate from it, and I get something like, the United States will step up to the cost of a new challenges of the American people that will share the fact that we created the problem. They were attacked, and so that they have to say that all the tasks of the final days of war, that I will not be able to get this done. Yeah, well, maybe that's slightly better than my N-gram language model. Still not perfect, you might say, but somewhat better, maybe? Did you have a question?
Yeah, so since we're training the model on a truncated set of the corpus, does that impose some kind of limitation on how much we can produce and still have some coherency and the meaning of the sentence we're creating, or
So I suggested we're going to chunk the text into 100-word units. So that's the limit of the amount of prior context that we're going to use. So that's a fair amount, 100 words. That's typically several sentences. But to the extent that you wanted to know even more about the further back context, you wouldn't be able to. And certainly that's one of the ways in which modern large language models are using far bigger context than that. They're now using thousands of words of prior context. Yeah, absolutely. It's a limit on how much far back context. So in some sense, actually, even though in theory a recurrent neural network can feed in an arbitrary length context, as soon as I say, practically we cut it into segments, actually that means we are making a Markov assumption again, and we're saying the further back context doesn't matter. Yeah. Okay, couple more examples. So instead of Barack Obama, I can feed in Harry Potter, which is a somewhat bigger corpus of text actually, and generate from that. And so I can get, sorry, Harry shouted, panicking. I'll leave those brooms in London, are they? No idea, said nearly headless Nick, casting low close by Cedric, carrying the last bit of treacle charms from Harry's shoulder. And to answer him, the common room perched upon it. 4 arms held a shining knob, from when the spider hadn't felt it seemed. He reached the teams too. Well, there you go. You can do other things as well. So you can train it on recipes and generate a recipe. This one's a recipe I don't suggest you try and cook, but it looks sort of like a recipe if you don't look very hard. Chocolate ranch barbecue. Categories: game, casseroles, cookies. Yield 6 servings, 2 tablespoons of Parmesan cheese chopped, 1 cup of coconut milk and 3 eggs beaten. Place each pasta over layers of lumps. Shape mixture into the moderate oven and simmer until firm. Serve hot in bodied fresh mustard, orange and cheese. Combine the cheese and salt together, the dough in a large skillet, and the ingredients and stir in the chocolate and pepper. Yeah, it's not exactly a very consistent recipe when it comes down to it. It sort of has a language of a recipe, but it's absolute. Maybe if I had scaled it more and had a bigger corpus, it would have done a bit better. But it's definitely not using the ingredients there are. Let's see, it's almost time today, so maybe about all I can do is I can do one more fun example, and then after that, I probably should do that bit at the start next time. So as a variant of building RNN language models, I mean, so far we've been building them over words. So our, token time steps over which you build it as words. I mean, actually you can use the idea of recurrent neural networks over any other size unit, and people have used them for other things. So people have used them in bioinformatics for things like DNA, for sort of having gene sequencing or protein sequencing or anything like that. But even staying with language, instead of building them over words, you can build them over characters, so that I'm generating a letter at a time rather than a word at a time. And so that can sometimes be useful because it allows us to sort of generate things that sort of look like words and perhaps have the structure of English words. And so similarly, there are other things that you can do. So before I initialized the hidden state, I said, you just have an initial hidden state. You can make it zeros if you want. Well, sometimes we're going to build a contextual RNN where we can initialize the hidden state with something else. So in particular, I can initialize the hidden state with the RGB values of a color. And so I can have initialize the hidden state with the color and generate character at a time the name of paint colors. And I can train a model based on a paint company's catalog of names of colors and their RGB of their colors. And then I can give it different paint colors, and it'll come up with names for them. And it actually does an excellent job. This one worked really well. Look at this. This one here is ghastly pink, power gray, navel tan, Bokko white, horrible gray, Homestar brown. Now, couldn't you just imagine finding all of these in a paint catalog? I mean, some of them are, there's some really good ones over here in the bottom, right? This color here is dope. And then this stoner blue, Burple simp, stanky bean, and turdly. Now, I think I've got a real business opportunity here in the paint company market for my recurrent neural network. Okay, I'll stop there for today and do more of the science of neural networks next time.